Hi, my name is Ajay. This is Physics 2, Lab 2, computational tape model. So for this lab, we're going to use code to model two charged pieces of tape exerting forces on each other and estimate the amount of charge needed for repulsion and equilibrium. So we're going to be using Coulomb's law and Newton's second law to do these calculations, and we're going to be modeling this using GlowScript. And as a result, we're going to calculate the electric and gravitational force, also with the electric charge. So some physics concepts we're going to use in Coulomb's law, which is equal to Coulomb's constant times two charged particles divided by the magnitude of their position, and as well as Newton's second law, F equals ma. In this case, it'll be negative mg for the gravitational force. So some initial conditions for this lab, we're going to be treating tape A as our system. You can do it the other way, but it's more complicated. And our surroundings are tape B and the Earth. Earth is going to act as a gravitational force on tape A. Here are our conditions, our mass, length, width of our tape, and also the distance that where it moved. These are all results and data taken from the last lab. And we're also going to assume no other external forces to minimize the complexity of our calculations, and since we don't know any other forces acting upon it. So here's our code model that we're going to be using. We're going to be using electric fields function, as well as treating everything as a line charge. Now for this, we wanted to add the masses to our top and bottom tape. We're assuming that they're the same mass just for the sake of complexity, and then also scaling our vectors so that we can see our results properly, as well as we wanted to see we needed to calculate our E field at different locations, and edit those formulas as such down here. So as a result, we have our two pieces of tape with the electric force pointing upwards with a magnitude of 1.6004 e to the negative 3 newtons. And this is pointing up to counteract the gravitational force, which is pointing in the opposite direction of the negative y direction down at 1.96004 e to the negative 3. And this is true because we know that from the experiment last week that the tape was at rest when we calculated the distance that it needed to be levitating or repelled. So since there's no acceleration or it's not moving, we can confirm that there would be a net zero force on this. And because we have no other forces that we're factoring in, these two magnitudes should be equal to each other. And then all the green arrows are the electric field of each bit of the tape. And then a charge of a single tape is 5.145 e to the negative 7 Newton coulombs. Now, some assumptions are made. This is from the last lab, but accidental discharge of the tape might cause our initial values for this lab to be incorrect. And we're also assuming that only forces acting on the tape are the electric and gravitational force, when there may in fact have been other forces. And we're also assuming that the tape we had made had an evenly distributed charge the entire length, when in fact a lot of most, if not all, objects do not have a uniform charge along their surface. So here's some what if questions. If we had modeled this as a single point charge, like in the previous lab, how would it differ? If we modeled this like a point charge, our charge would be 4.27748 e to the negative 7 coulombs versus the 5.145 e to the negative 7 coulombs from the computational model. And a point charge model is less accurate than the line charge model because there's a charge distribution on an entire piece of tape is more accurate than an oversimplification of one point, just because of the location of different charges, and it accounts for variation in the charge density along the entire length versus just having a point right in the middle. And which charge is more likely to be closer to the real value and why? It would be the computational model with the charge distribution. And again, that's because it's too hard to assume that we're going to be having a charge that's directly in the center versus along the entire length of the tape. That is it. Thank you.